So these will be the three classes. You can definitely look at the slides. I'll go back to the slides in a moment, but let's now take a look. Let's now highlight the keywords of abstract, right? You can see, first of all, we got abstract before the class over here, and also we got abstract over here. Okay, let me now just go directly to the abstract. Okay, so here, this abstract over here at the method level, right? You can see this abstract over here is at the class level. Let's talk about the method level abstract first. Okay, the abstract over here simply means implementation. The implementation is delayed or deferred to the subclasses. Right? It's as simple as that. And over here you can see this part here. After declaring the method, you can see what we did was after saying abstract, the return type, and also the method name. So no parameters, no input parameter for the method. We simply just got semicolon, right? You can see we are doing this rather than simply just empty brackets of empty implementation, right? I really want you to contrast this. I really want you to contrast this together with abstract versus the initial design when I say simply empty body implementation. So they are different. But I would say this is conceptually much cleaner, because as soon as we say abstract over here, that tells us we are not committed to defining some implementation at this level. We're delaying that to the subclasses. Okay, and that's about the method level abstract, meaning that we simply delayed the implementation to the subclasses. So what about the class level abstract over here? So the class level abstract over here, let me try to write it here. Okay, so that one simply means over here, at least one method is abstract. As long as within the context of this particular class, as long as at least one of the methods is actually abstract, in this case, indeed, the area, at least it is abstract. So that means the class itself is abstract. And I'll talk about the consequence in just a moment. Okay, and let's now take a look at subclasses over here. You can see we already declare the get area to be abstract. That means we're expecting the subclasses to actually declare to make some implementation. Especially over here, you can see this one here. We are supplying some implementation for this method here, and also we are supplying some implementation for this one here. So that means the get area at the subclass level is no longer abstract. Okay, it's also very important to note. Okay, so get area over here, and also get area over here. Okay, so at the subclass level, no longer abstract, because you can see we got some implementation over here, and also we got some implementation over here. Okay, that's what we got. Okay, so let's now take a look at the Polygon class very carefully. Okay, we already spoke about what attributes you would need conceptually, but let's take a look at how you should define the Java code very quickly. So this is the declaration for the attributes, simply an array of double for the sides. And also this is a constructor, right? So with for initializing some polygon, we simply pass an array of double, and then we simply initialize the array accordingly. We'll see exactly how this works when we see some test cases. And for the grow method, we make it very easy. We simply, as I said before, simply go over the array, and then the array of sides, and then just increment each side by 1. That's what we meant by grow, simple one. For example, you can think about, let's say here, if we have some triangle like this, okay, let's say, I don't know, maybe 1, 2, actually, let's say 1, 3, and let's say 3.5, okay? Let's say this is our triangle, okay? What's happening here is you can see 1 plus 3 larger than 3.5, right? 3 plus 3.5 larger than 1. And also 1 plus 3.5 also larger than 3. So that's a valid triangle, okay? What does it really mean to grow this triangle? if I actually want to grow the triangle, I'm simply just going to increment each side by 1. So what's going to happen is we're going to have a slightly different triangle. May not be to the scale, but I just want to illustrate to you, right? 1 plus 1 is going to be 2. 3 plus 1 is going to be 4. 3.5 plus 1 is going to be 4.5. Is this still a valid triangle? Let's see. 2 plus 4, larger than this. Good. 4 plus 4.5, larger than this. Good. 2 plus 4.5, also larger than this. So it's still a valid triangle. So this is about growing by incrementing each side accordingly. Okay, and then getting the perimeter over here, that's very easy. You simply just add up all the sides. I'll let you go over this loop. It's rather easy. Okay, and also for get area over here, you can see we are trying to override this method. In some way, it's like an increment. Well, but if you want to think about override, that's fine. You know, it may not be as not as accurate. This get area here is actually abstract. So that means we're expecting the subclasses to really implement the get area method. Let's take a look more closely. Okay, let's say in the case of triangle, you can see rectangle first. You can see rectangle extends polygon, right? Pretty much like how we implement the inheritance earlier. And then you can see for rectangle, for the constructor over here, we simply say see what's the length and what's the width. And then we're going to use the length and the width to actually initialize the array. So what we do is we simply use a super keyword over here. So this call to the super is actually going to call the parent version for the constructor, which is over here, this part over here, right? It's really important for you to see that. Let me see if I can actually try to, let me just try to show to you. All right, it's actually calling this one here. And then you can see we simply passing an array of length 4 over here. So that means that's for initializing a triangle. Similarly, you can see in the case of triangle constructor, we're also calling super, calling that default constructor, right? That's inherited from the parent class. And in this case, we are doing size 3. So you can see 3 versus 4. That's something I'll try to visualize to you a little bit later. For this one here, you can see this one actually is referred to by the super keyword. Okay, and let's see how can we initialize the array separately. For example, if I simply try to create a rectangle, let's say this is 3. Just for example, if this is 3, this is 4. So how do I create the array? In that case, the array will look something like it's going to be of size 4. So 0, 1, 2. And also 3. So the way to do it is the length followed by width, followed by length, followed by width. So it's going to be 3, 4, 3, 4. So 3, 4, 3, and 4. Right? That's what's going to happen. And then when you calculate it, how do you calculate the area? You simply say size at index 0 multiplied by size at 1. Right? So it's going to be this multiplied by that. So that's going to be how we calculate the area, right? This one's rather easy. Okay. What about the triangle? It will be very similar, except that we have to get 3 sides rather than 4 sides. Let's see how that's going to happen. You can see here we got a new double here. You can see we are passing 3 inputs to the triangle constructor. Let's say for example 3, 4, and 5. If we simply say side 1 is 3 and this one is 4, this one is 5. So what's going to happen is we're going to initialize the value in the size array of size 3, 0, 1, and 2. You can see here we're passing a double array of size 3. And then index 0, index 1, and index 2, right? So it should be 3, 4, and 5. So 3, 4, and also 5. So these are the 3 members in the array. And for this part over here, this part is exactly implementing faithfully this formula over here. Okay, and I'll let you see exactly how that's done, right? I'll leave that to you as a self-study, right? That should be rather easy. The only thing that which I assume you actually learn from the first year is how you can use this methods from the math classes. Okay, so for every method in the math class is actually so-called static method, meaning that you can simply just invoke them by using the math class name without creating a math object. You don't need to, because every method there is static. Okay, so square root is actually a static method in the math class, right? If you have any doubts about the math class, you can get in touch with me, but that's how you calculate the square root for some number. Okay, so this part over here corresponding to exactly this part over here, okay, that I spoke about conceptually. Okay, so that's a very quick walkthrough about the 3 classes. Study them very carefully, and then let's now take a look at quickly some example code. So in this example, we have a single reference variable, P, over here. And P is going to be polymorphic, given that its static type is general enough. You can see static type is actually Polygon, which we declare over here. Right? You can see abstract class Polygon. And the reason that Polygon class is actually abstract is actually because at least one of its method is actually abstract. Specifically, you can see the method getArea is actually abstract, right? And of course, based on our design earlier, you can just remember there are actually 2 subclasses underneath the Polygon. One is rectangle, and the other one is triangle. Just remember. And of course, each one of them is going to implement the getArea accordingly, according to the algorithm that we spoke about. Okay, so let's now take a look at the example code. Only a few lines. Let's look at the first one. Okay, the first one over here, let me use pink. Okay, and here we say P is assigned to new rectangle. Okay, so we're calling the constructor for rectangle, right? If you actually recall how we declare that, right? If you go back to the definition for rectangle class over here, you can see the first line is simply going to call the super, meaning that we're going to call the parent version over here, right? And then it's going to have a new double array of size 4. And later on, we're going to see size 3 for triangle accordingly, right? Just remember that. That's how you draw the connection. And let's now visualize the creation of a rectangle object by calling this constructor, which I just showed to you. So by calling the rectangle constructor, so here we got 3 and 4. So remember, this is the width and this is the length. So what's going to happen is when we create this rectangle objects, the size would just be initialized to be a 4 elements array. 1, 2, 3, 4. And then 3 and 4, as I illustrated before, is going to be 3, 4, and 3, 4. All right, so that's something you already knew. And of course, at this we have to store its address into the polymorphic reference variable P over here, right? So P is going to be assigned the address of this particular object, right? So what's going to happen is P is now going to point to wherever this rectangle object is in the memory. A quick check on our knowledge about the inheritance. Is this valid over here, right? So this is the question. Is this a valid substitution? All right, you should really pause the video and write down your answer to my question. All right, assuming that you thought about it, this one should be valid. Okay, yes. But why? It's because the proposed dynamic type rectangle over here can fulfill the static type for P, which is Polygon, because rectangle is a descending class of Polygon according to the inheritance hierarchy that we have. Okay, it's a very important review question for you, because dynamic type rectangle is a descending class of P's static type, which is Polygon. Right? So that's why having this P over here declared to be the parent type is very beneficial, because now for the because of polymorphism, we can allow any dynamic types that would be a descending class of Polygon. In this case, rectangle and triangle. Right? It's very important. All right, let's now go further. So at this point, what is the dynamic type for P? It should be pointing to some rectangle object, so it should be a rectangle as the dynamic type, right? So now when we do p.getPerimeter and also p.getArea, according to dynamic binding, we should really know which version of the method should be called, right? What about, okay, so here for P, what should be the dynamic type? So here, dynamic type we know is should be rectangle. Meaning that if you try P instance of rectangle, it should be true. Instance of rectangle, it should be true. All right, it's something very quickly to remind you. All right, so knowing that dynamic type is actually rectangle, so but when we say get perimeter over here, which version are we going to call? Right, this one here. Let me just use blue. Let me use pink. If we say get parameter over here, since the get parameter is actually used verbatim in both rectangle and triangle classes, so only this version will be called. And get area over here was actually abstract in the case of the polygon. So that means we should really go for the dynamic type, which is rectangle. So that should be invoked from this version over here, right? So hopefully you're still following. So get parameter actually will be from Polygon version. Polygon version. And also the get area should be the rectangle version. Right? Of course, you can do the math about the calculation. Right? I'm not going to waste your time over here. All right. Similarly, let's say we want to reassign the reference variable to change its dynamic type. Right? Let's now maybe let me use orange over here. Let's say we are trying to do this line over here. Let's say how do we do that? Let's take a look. So this one here is going to this part here is going to call the constructor from the triangle class. Right? In that case, we got 3, 4, and 5. So we are creating this triangle objects, and then the array should be initialized to be size 3 again. So this definition here comes from this line over here, which you should really study carefully. All right, and then so that one should be 3, 4, and 5. So 3, 4, and also 5 over here. All right. Again, that's polymorphism because you can see this is actually valid because triangle is a descending class of the static type of P, right? Similar reason as this one here. I'll let you write it down as an exercise, okay? And let's now try to look at P.get parameter and also P.get area. I want you to compare and contrast. This line here is identical to this line over here, but the context object P has different dynamic type. Agree? And also P.get area and also P.get area identical lines. However, the context object P have different dynamic type, right? Let's now try to write it down. Okay, so P here is a context objects, and then we know that dynamic type. Oh, by the way, let me just change the dynamic type first before we do anything further. So when we do this substitution here, that means we know that's valid. So P rather than pointing to rectangle, it is now going to point to triangle. So now this will be the new dynamic type, which is triangle, right? So dynamic type will be triangle. And if you try P.instance of rectangle, at this point is going to be false, right? Just remember the same expression over here, depending on where you are in the code, it may either evaluate to true or evaluate to false, right? So remember this P.instance of rectangle, if you try to evaluate it, maybe before this reassignment occur, it's going to be true. As soon as after this reassignment occur, if you evaluate it again, it's going to be false because now P instance of triangle should be true, right? It's something also very important to show to you. Okay, so what about version of the method being called? So P.get parameter, right? Even though the dynamic type is actually triangle, but there's only one version for the get parameter. So we are still calling that version there. Still that version. Okay, so this one here, so we're still going to get Polygon version. Polygon version. And what about P.get area? Dynamic type is actually triangle, and we're going to call the version that's actually overridden in the triangle. Remember, that's the one using the Heron's formula over here, right? That's something I'll let you study about why it is implementing that square root that we spoke about earlier. If you got any doubts, you can let me know. Okay, so this part over here is the triangle version of the get area. Triangle version over here. All right, so that's a very simple piece of code just to show to you. Again, polymorphism about the two variable substitutions, why they are valid. That's polymorphism. And also for dynamic binding, depending on the dynamic type, this versus that of the context objects, you may just invoke different versions of the method depending on what the dynamic type is. For example, here, dynamic type is actually rectangle, so that means you're going to invoke the rectangle get area formula. As opposed to, in this case, the dynamic type for P, the context object, is actually triangle, so that's why I'm going to use the one that implements the Harris formula. Okay, so let's now go back to the slides to see if there's any point I missed. All right, so we talk about Polygon, right? The abstract class, the parent class, and there's one important point which I haven't said just yet. Let's now go over that. We say Polygon, given that it's actually abstract, it cannot be used as a dynamic type. So what do I mean by this? Okay, let me just go back here. Let's use the same example. So this will be the perfect place to actually illustrate this. Okay, remember we already declared polygon P over here, right? Let's now try the following. Can I say P over here is assigned to new objects over here rather than rectangle or triangle, which we already illustrated? What about just polygon? All right, is this valid or not? Okay, pause the video and think about it. All right, assuming that you thought about it, you might think this will be valid because of the following reason. Polygon, the proposed dynamic type, can fulfill the expectation for the static type polygon because polygon is simply a descending class of itself. That might be your reasoning. I would say if you thought about that way, it's not too bad. At least you still remember the rules for the substitution, also about the expectation, the intuition. However, that's not the right way to think about it, right? For even more basic reason. So the polygon over here simply cannot be used. It's not valid. So it's invalid. Okay, let's see why. Okay, remember how we actually prove by contradiction when we talk about the intuition for polymorphism. Why don't we say, what if this is valid? Okay, let's assume it is valid. Okay, oh, let's now simply assume it is valid. Assume it is valid. And we're going to see how this assumption can lead to disaster. Okay, if this is valid, that means at the runtime we're going to create this polygon objects over here, right? So what's going to happen is, so P, okay, let me just put it there. You know what? Let me just put this reasoning over here, all the way to over here, so you can see the. Oh, actually, let me do it again. Okay. Okay, let me now actually get this to there. Okay, over here. Okay, let me just make it a little bit smaller. Okay, let's assume this is valid. If it was valid, so that means we can actually say P, rather than pointing to this, we can actually let it point to some polygon objects over here, right? If it is a polygon objects. Let's put polygon over here. Polygon, okay? And polygon, remember, we got size, we got grow method, we got get parameter. However, the get area here, remember that one is abstract. All right. Specifically, you can let me just put a star here. That simply means abstract, and then get area. Get area over here. Right, just remember that. And assuming that it is valid, so that means we can call methods on P. So now, if we say P dot get area, first of all, should we be allowed to actually call this method? The answer is we should be, because P static type is actually polygon. Part of its expectation is simply declared as get area. However, if we say P.get area right now, we are going to invoke this abstract version of the get area, which contains nothing. So that means the program is still going to crash. All right. So that means it is going to crash because get area over here is abstract. Right? Given that having the assumption that it is valid will lead to some crash, some disaster. So our initial assumption that it is valid should be inappropriate. So the answer should be, it should be invalid. So that means every time you want to have a dynamic type after the new keyword, you want to make sure it is not an abstract class. It's a very important idea to think about. to actually understand as well. Let me just write one more note over here for you. Or you can think about abstract class cannot be used as a dynamic type because it has at least one method unimplemented, meaning that if you try to invoke it at the runtime, it's going to crash. So that's why it should not even compile. Has at least one method that's unimplemented, meaning that it's abstract, right? That's the very definition for abstract class. Okay, let me just highlight it. Abstract class cannot be used as a dynamic type because at least one method that's unimplemented. Okay, I will encourage you to actually try to write this line over here and say new Polygon. You will notice that there will be a compilation error at Eclipse as a red underline. That's something I'd like you to try. Okay, let's now move on. And later on, we will see for the similar reasoning, also interface classes cannot be used as a dynamic type. That's something we'll see later. Okay, it's forbidden, so it's not going to compile. And so that's rectangle class, and we spoke about, and that's a triangle class. Both rectangle and triangle, they can be used as dynamic types for sure because they got all the methods implemented. Okay, and we can talk. Okay, so that's up to now. We have spoken about all the three classes. Also, we have spoken about some lines of example. Let's now move on to another example, which is about a polygon collector.